Hi, I'm Antonio Sala, and in this video we'll continue with the case study on manipulated uncontrolled variable selection. So we will discuss, in this case, the steady-state partial disturbance rejection with SVD techniques, the geometry of ellipses and the spheres. In an immediately previous video, in this case study, we discussed the polyhedron approach to the same problem. So let's see which are the similarities and differences. This was our system model, 2 control variables, 3 manipulated ones, and 2 main disturbances, which must be counteracted to minimize the residual deviation of y. These are the transfer function matrices G and H. In here we'll just discuss the DC gain with these admissible increments of manipulated variables, choosing the worst case minimum absolute value. We crafted an input scaling matrix as this one, and then in setpoint tracking videos we wished the output increments to be large, and we built this output scaling matrix. However, this matrix will not be valid for disturbance rejection. In the videos we dealt with complete total disturbance rejection, then it worked whatever output scaling we used, because 0 in any scaled units will keep being 0. However, in partial disturbance rejection, we'll need to change this output scaling matrix, so we will forget about this EY. So this scale gain matrix we used in earlier videos will no longer be valid here. We'll later on see which one is the one we should use. The input scaling matrix will keep being valid, as well as the disturbance scaling matrix we did in the total rejection case, because we had these maximum disturbance increments and we chose the worst case maximum absolute value to build this disturbance scaling matrix. So our assumptions will be that the physical disturbances will attain values given by the unit sphere in scaled units times this scaling matrix. Good. But then when we discuss partial disturbance rejection, which is the case now, we had these inequalities that define some polyhedra in which my input, output disturbance, whatever should be. But now we need to make a scaling based on the numbers in this problem statement, in which first variable may have a residual error in between of minus 0.1 or plus 0.2, but as the SVD geometry, the geometry of spheres, must be symmetric around the origin, then the worst case will be the minimum error. So we will wish our first variable error to be less than 0.1, and likewise our second variable error, which in the polyhedron approach was allowed to range between minus 0.15 and plus 0.25. Now the worst case symmetric choice will be requiring the second error being lower than 0.15. So good. With these two numbers we will craft this residual error scaling matrix, so that even if the residual error, when I am able to compute some U optimal for the disturbance rejection task, will have this equation, well, with a suitable scaling we will interpret our problem in scaled unit as follows. When disturbances scaled lie in the unit sphere, we must be able to find an optimal U in the unit sphere scaled, such that the residual deviation epsilon scaled is inside the unit sphere. So now that everything has been translated to the unit sphere, we will be able to carry out some SVD, pseudo-inverse and stuff like that to solve the problem. So we are going to solve the problem trying to achieve this inequality. Why? Well, because we don't have any control over what values disturbance take, so they may be anywhere. But the thing is that our control action must be such that epsilon squared, let's say, is less than 1, and u squared is less than 1. One way to do that, maybe a little bit conservative, a square of 2 conservatism may arise, but anyway, if epsilon squared plus u squared is less than 1, then necessarily both epsilon scaled and u scaled are below 1, and then with the expression I have highlighted in blue, we may make an extended vector with epsilon and u and force it to be in the 4-dimensional unit sphere. Indeed, that's what we are saying here. If we define some nu stacking the residual error and the input, then it's 5-dimensional. I said 4 earlier on, but it was 5-dimensional. So we have 2 errors and 3 manipulated variables. Then our goal can be translated to achieving nu squared less than 1 for any d-scaled such that its norm is less than 1. And we will achieve that with some pseudo-inverse stuff, which is least squares, weighted least squares. Weights are those from the scalings, of course. So let's delve into the details. Which are the equations for this nu? Well, the first component, error, is gu plus hd, and the second component, u, is, well, identity times u plus 0 times t. So for convenience, I will call the first matrix t, and the second matrix will be denoted by q. Good. What's next? Well, which u should we compute to minimize the norm of nu, to minimize the sum of the squares of the components of nu? Well, that's a least squares problem. Indeed, if I think in this system of equations, let's say, then I have 3 decision variables, u, and 5 equations, because t and q have 5 rows. Nu is 5-dimensional. So I cannot achieve 0 fitting error in most cases in this system with 3 equations and 3 unknowns, 3 decision variables. So if I try to approximate as much as possible tu to minus qd with pseudo-inverse, with least squares, then that will be the solution of the problem of minimizing nu. I would be very happy if this tu were equal to minus qd, but that will not be possible, so I will try to approximate it as much as I can with least squares, and that solution will minimize the norm of nu. So good, which is the solution? Well, that solution to this weighted least squares problem is the pseudo-inverse of t, denoted by t dagger, multiplied by minus qd scaled. So good. The thing is that what we wish is nu being less than 1, so I need to compute nu if I use this optimal u in there. So indeed, replacing this expression in here, I will have some minus t pseudo-inverse q d scaled, and then this q d scaled will end up being responsible for this just 1 times q times d scaled. So this is the optimal value of nu, the one with smallest norm from all possible manipulated inputs u, and just extracting common factor q, I will get this expression in here. So now we can state our main conclusion from the theoretical development, which is that if this matrix I am encircling in this blue rectangle has all its singular values less than 1, then when d scaled ranges in the unit sphere, then nu will also be inside the unit sphere in 5D. So our problem will be deemed feasible, and that's it. The only thing to do now in our example is just compute t pseudo-inverse, and q, and compute the SVD of this matrix. So let's do it. First, we compute the new scaling matrices in which the output scaling has changed to this output scaling matrix related to the maximum errors I wish to have in this new problem. So once I have those scaling stuffs, well, these were t and q, g identity h0, so this is t and this is q. Good. Then I need to compute I minus t pseudo-inverse times q and carry out singular value decomposition. So this is the matrix I wish. Anyway, for conceptual clarity, this pseudo-inverse t of q is this feed-forward, let's say, matrix that I would use in actual implementation if my disturbances were measurable or at least observable with some observer. But this is the one I wish to compute the singular values. So I name it thing less than 1, and if I compute the SVD, then all singular values are lower than 1, so my problem of partial disturbance rejection is feasible. Of course it is, because even the total disturbance rejection was feasible. So no surprise here. We will now compute, as we did in earlier videos, the margin in which disturbances could be larger and still keep my error within the prescribed bounds. For instance, as the maximum gain of this matrix is 0.54, then my disturbances can be 1.84 times larger, and even in that case, when multiplied by this matrix, they will still give results less than 1. So this would be, let's say, the extra leg room we have when considering partial disturbance rejection and still keeping feasibility. If we recall, in the polyhedron geometry, we had a margin of 2.08 because, polyhedron geometry was able to consider non-symmetrical bounds in disturbances and in inputs, so the analysis was more accurate. In here, instead of 2.08, we get a margin of 1.8. That's what we lose from discussing symmetric spheres instead of asymmetric polyhedra. But the analysis in the polyhedra geometry cannot extend to transient, whereas this analysis of pseudo-inverse and singular values can indeed be extended to transient behavior, and in fact it's the motivating idea for H-infinity control, in particular mixed sensitivity algorithms. But of course these algorithms are not in the scope of this video. We are just pseudo-inverse weighted least squares in a steady state. A last remark discusses that, what we wish to be less than 1 is element by element of these matrices. So we might even consider dividing this into these two submatrices so that the error matrix, the upper one, has SVD less than 1, and the control action matrix, the bottom 3 rows, has SVD less than 1 to check that errors and controls are in the unit sphere. So that would refine a little bit this bound, but of course pseudo-inverse, the only computation that can do is this one, but in order to refine the margin, instead of 1.04, we could just think in the SVD of the error, it's small, and the SVD of the 3 bottom rows of the needed control action, which is 0.535, whose inverse is 1.87, so we can sort of refine a little bit instead of 84, 87, and row by row, the SVD of each of the 5 rows less than 1 would mean that each error and each control action would be less than 1 for unit sphere disturbances. So that would be the closest to the polyhedra approach. And in fact, the SVD of one row is just the norm of that row. The thing is that, well, we have 5 SVDs, so 0.53 is the first manipulated variable, the one that suffers the most in a worst case situation. So the margin with this kind of last tricks on the SVD geometry could be raised to 1.88. But okay, pseudo-inverse does not directly optimize this. Pseudo-inverse minimizes the norm of the 5D new vector, so it minimizes this number, 0.54, let's say. And the other thing are, last minute remarks and observations that can change the third significant digit from 84 to 88, but nothing really important. So theory usually dismisses those kind of last tricks. The thing is that, in summary, we did a pseudo-inverse based weighted least squares approach to the problem. As it was feasible with the inverse of the maximum gain, we obtained a margin by which disturbances could be increased, but we were conservative with respect to the polyhedron approach in previous videos. So this is it. We end the video here. Thanks for watching.